So good evening everyone, and welcome to the last lecture of our course on neural networks. And today we are going to consider how do we run a neural network on an embedded device. So I will show you today what do we do with neural networks to fit better to the embedded devices, and we will try to run our network on a device like this one. So first we start with some theory, and then we will consider running that network on a device. So here we have some code. I will need a few different frameworks for today's lecture. We mostly used PyTorch, but today we will use a little bit of TensorFlow. We will not code neural networks for the TensorFlow, but the thing is that certain interesting methods that make the neural network more suitable for embedded devices, they are implemented in the the TensorFlow. So we will need it just for a little bit, and we will convert our networks to that sort of format. So before we start, here you see some part of code I'm running in Google Colab, so you will probably be able to find that after the lecture. That setups a certain environment that we need, setups all the frameworks, and I should tell you it runs for a long time, so probably you will need to wait for a while, something like 20 or 15 minutes at least. So I have run that beforehand, so you see now it's stopped, and I will be able to show you all the rest of the code. So good. The first problem that we tackle when we are trying to fit our neural network to an embedded device is the problem that embedded systems have pretty limited operative memory, or pretty limited RAM. So we need to do something. We need to reduce somehow the size of the model and the memory that it consumes while maintaining some acceptable accuracy. There are different methods to do that, and few of them I will consider today. I guess the ones that will give you the the most of the result. So what kind of methods do we have? First of all, that's so-called pruning or weight sparsification. So that removes some of the unnecessary weights of the neurons. You may find two different branches of that pruning. One is called unstructured pruning. That's when you are just removing some zero or small weights, and you get sparse matrices after the pruning procedure. The problem is that it is inefficient if you don't have any hardware support for the sparse matrices and sparse matrices multiplications. If you don't have that, that won't help you to do anything. Or you can do so-called structured pruning. That will remove entire filters, channels, or even layers from your neural network. So it may happen that we have trained our neural network and we have certain channels that contain pretty small values that are close to zero or something like that, and we may want to remove them. Of course, this leads to some changes in the architecture of the neural network. That's a little bit more complicated, and I'm not sure whether we have some nice packages, nice libraries to do that, but anyway, today I will show you both unstructured pruning and structured pruning, and we will try to make our neural network a little bit smaller, and I will show you where it leads us to. The second thing is the quantization. Quantization is often used for running neural networks on embedded devices. The idea is that when we are storing our coefficients, we are using mostly, if we train our neural network on some server or on the computer, we use, for example, float 32 or float 64. But when getting to the embedded device, we might think to change that, for example, to int 8 or just one byte for each single coefficient in the kernels of our convolutions or other coefficients in our neural network. In some cases, even int4 may be considered. Of course, you need some sort of retraining after that conversion, but anyway, that pretty works, and I will show you today the quantization approach as well. Of course, there is another branch like quantization aware training. That's when you simulate quantization during training for better accuracy. So you are training neural network with already set goal that you want to get at the end of the day quantized neural network. Of course, that really helps you with the with RAM and with memory usage. Approach number 3: knowledge distillation. This is an interesting approach that when you have, suppose you have trained some large neural network, and you have this neural network, it works pretty good, and now you see that you cannot fit that neural network onto your embedded device. But you may find some smaller architecture and train it not from scratch, but basing on the outputs of the large neural network. I will show you this approach as well. So that's pretty interesting. Let me draw that just a sketch of it. So suppose you have some very large neural network that contains many layers, and we have some input here, and here we have some output. Suppose, as for today's lecture, we will have some larger neural network that can recognize numbers. So that generates for us some numbers, 10 different numbers that are interpreted as the probabilities of getting digit 0, digit 1, 2, 3, and so forth up to 9. And then we give this result, the maximal the digit with the maximal probability, we give that to user. Now suppose I want to fit that into an embedded device, but it is, let's say, too large for that device. What can I do? I can take some smaller network with much fewer layers, maybe even different layers, and I train it to get these input and to give the same output, but before we had taken max probability. And if I train this network not on the data set, but on the inputs and outputs of the large network, it may happen that its quality will be on par with the quality of the large neural network. That happens because the output of the large neural network contains more information than the ground truth in our data set. So our data set contains only one number. It tells you if I have put in here an image of a 3, I should get as output 3. So the loss function for the large neural network compares this output with the ground truth. So here is input, here is ground truth. So let me draw this somehow that we see this is an image. So this is an image. It's getting into the neural network. We get some output. We are getting these sort of probabilities, and we are taking the digit with the maximal probability, and we compare that with the ground truth. And that's basically gives us loss function for large neural network. But if I train this one, I take this input and I compare it for the training. I need to compare it with this output. So I take this output, I take the output of the small neural network, I compare them, with the idea that they have the same input. And this will produce me loss function for small neural network. We will see that in code today. Okay, what else do we have? Low rank factorization. When we are performing all that operations on neural networks, that's in some sense that are operations on matrices. So in some cases we may want to split our matrices into a product of two or more matrices with a lower rank. So I hope you know what is a rank. So suppose just a very simple case. Let me have a fully connected layer. So I have some input, I have certain neurons in that layer, and each neuron is taking all the inputs and generates some output. Basically each of them has different weights for each of the inputs. You can think of it like if I have an input vector. So here are my inputs, input 1, 2, 3, so on. So these are my input 1, input 2, input 3, so some numbers coming here. And I can multiply them by a matrix of weights. So I might multiply them by some W11, W12, W13, and so on. What are these? And here I have W21, W31, 41, 51. So what do I have, and so on. So what do I have here? When I multiply these numbers with this matrix, I get a new vector that will contain something like W11 I1 plus W21 I2 plus W31 I3 and so on, and I will get the whole vector. So you might see that the entries in this vector are actually the outputs here from this layer. So I'm not sure if this marker works. If it does, so let me circle these and show you that this is basically the same. So my operation, that's basically a multiplication with a matrix. And the thing is that this matrix may have certain rank, or it can be approximated with a matrix of some lower rank. What does it mean? A matrix of lower rank can be represented as the product of two different matrices. Suppose, for simplicity, this matrix had a rank 1. So what does it mean? It can be represented as a product of matrix, I guess, of this size times this. So with basically two vectors. I have certain entries here, I have certain entries here. I don't know, let's call them A1, A2, and so on. Here will be B1, B2, B3, and so on. So now each of these entries, this one, for example, that will be A1 times B1, this will be A1 times B2, and so on. That is possible if this matrix has some lower rank, or we can approximate it with certain methods like singular value decomposition and so on with the matrix of a little bit lower rank. Of course, this is an extreme case of rank 1, so that's extreme case of rank 1. But anyway, for larger ranks, you might get the idea how that will work. So here's what we have. And what's interesting here, suppose that I'm still performing this sort of multiplication. I will need to multiply this vector. I can multiply it first with this vector. This is just a number of multiplication that is equal to the number of inputs. I will get some number, I will multiply it with this vector, and I will get my result. So that's what we have. I guess these vectors should be, I need to a little bit correct myself. This will be not a vector column, but a vector row. Let me write just transpose here, so that will be a vector row. So you see that in this case, the number of multiplication, it's the number of entries for each of these rows times number of inputs times number of outputs, and you need to do many summations, while in this case the number of operations performed is much lower. So it's really beneficial to make these sort of decompositions. So we can do that. And that works well for some sort of fully connected layers like this one. You can do that for convolutional layers and in some different cases. We can do so-called weight sharing or clustering. I will not show these methods as well as factorization today, but I want you to know about it. So this is a method when you are creating groups of similar weights. You are looking at your neural network, you are finding similar weights, and instead of storing all the weights, you can store just center of the cluster, some mean value of these clustered weights, and some sort of indices. So you are just indexing the weights, and you are not keeping all of them, all the variety of these weights, but only that sort of cluster centers. And that reduces the storage by replacing float values with small integer codes, because you need to index that just with a small integer. Maybe you need just 1 byte to index all that cluster centers. And that's often combined with Huffman encoding. I will not get into that today. That's just some sort of algorithm that allows you to compress your data a little bit based on the entropy, and these coding may be used together with that. Of course, you can use some more powerful methods like neural architecture search for efficiency. So when you use some algorithms, some meta algorithms that are trying different architectures of neural networks and are trying to find you the best architecture that will fit your device and your demands. And of course, there are some other optimizations that you can find, like operator fusion, when you combine multiple layers into one, like convolution plus batch norm plus ReLU, or you can use some mixed precision during training and inference. So you keep some layers with higher precision where you need that, and some layers you can a little bit quantize and use some lower precision. You can use some hardware-aware optimization, like Taylor kernels for specific DSP or MCU accelerators, or you can use some model caching and on-device pre-computation. So that's are all the methods you can use, and maybe there are some more, but these are, I guess, the most used methods that you may need if you need to fit your neural network into the embedded device. Good. So now, with that being said, let's try to do some of these methods on the neural network. So first of all, I will start some code. These are some functions that we need for training a neural network. I will not get into the details of these and some sort of plotting. I will not get into the details of this code because we have already considered on our previous lectures how do we train a neural network, and we have even constructed some neural networks and trained them, so not going into that. Some code for visualization, saving and loading, and calculating certain metrics. So we will use some accuracy, precision, recall, F1 score, and we will check whether our neural networks are performing good or not, and if we are do, and if you are using some methods to fit them into the embedded device, of course we will want to check whether we haven't broken our neural network. So is it still good? So what's the quality, and so on. So here I'm starting all these codes. We will work once again with our LeNet example. I think I will use this time 28 by 28 images, and we will try to recognize different digits with that sort of LeNet. We will construct a very simple neural network. So here it is. We have considered pretty similar networks before, and that looks pretty similar to the LeNet network. So here you see a convolutional layer, ReLU, one more convolution, one more ReLU, max pool. This just changes shape, and here you see a fully connected layer. This is in here it's called lazy linear, which means it calculates the number of the inputs on its own. When we were using in previous lectures, we have used some different layers, and we needed to enter the number of input channels explicitly. Here you see the very simple operation forward. That's because I have this layer stack that is created with the NN sequential, which means that all layers are sequential. So I'm just sending some input into the layer, getting output, and sending this output to the next layer, and so on, so on, so on. So no residual connections, nothing really fancy, nothing complicated. So the simplest neural network you can ever think of. So here I am creating the model. So here is our model. We have some input shapes, some output, some parameters, nothing really fancy. Here I want to show you once again the structure of the neural network. So here it is. Here we have some input tensor. That's an image 28 by 28. It gets into the convolutional layer. So here you see the input, one image. The output are 10 channels. That have, of course, size like 28, like images 28 by 28. Here we get through activation function ReLU. Then we get to another convolutional layer, gets 10 inputs, sends 10 outputs, nothing changes. We get through ReLU. Here is max pool. Here you see the size have got smaller. So here we have image 28 by 28, and here we have just half of that size, like 14 times 14. And then we are just changing our shape. So if you multiply these numbers, you will get 1960. So that's 10 channels, 14 by 14 image. And this is the input for the fully connected layer that generates 47 outputs. So 47, that's because we have included not only the digits 0 to 9, but also some letters of the Latin alphabet, so some letters of English alphabet, and we have them in the data set. We will perform training. Once again, we use categorical cross entropy function, and here it is. And we have some ground truths and softmax outputs. We have considered this sort of training in the previous lectures, so I will not get into really deep details here. The only thing to notice that some sort of recap of our first lecture. Here I tried to rewrite the formulae for each of the layers. And here you see that I can represent my neural network as some sort of a function. So the function that is a composition of convolution, ReLU, max pool, linear, and each of them can be represented in this sort of mathematical form. So here we have convolution represented with all these sums. Here we have ReLU, where theta is the Heaviside function, and here we have max pool, and so on. So you see that each neural network is just a large function with certain parameters, and we are searching for that parameter. So that's basically the architecture defines us a family of functions, and we are searching for the exact function by by searching for the best parameters that we can use to solve our problem. Here we have training. I'm not getting into much of the details here because we have already trained neural network. So let me just start this training. I guess it takes a little while, something like 10 minutes. Welcome back. So we have trained our neural network. That takes, as you see, 9 minutes. So here are the results of our training. We had just 3 epochs, and here you see the loss on the train set and the loss on the test set. So here you see that loss is down. That's pretty good, which means that our neural network is training and we are getting some results. And here you see the train and test accuracy. So here you see we started to train our network. Here we see our how our accuracy grows, and here we see that on the train and the test sets. That's pretty good. Okay, so let's test our quality a little bit more. So now I'm running some code that will print me certain parameters like precision, recall, and give me the confusion matrix, so we can check the quality of whatever we have done. So here we see accuracy 83%, 85 precision, recall 83, and F1 score 84. And here you see the confusion matrix. So here are our classes. These are different English letters and digits. These are true labels and predicted labels. And you might see that the matrix is almost diagonal, which means that we have a pretty reasonable quality for such a small neural network. Of course, in practice you will have much larger neural networks, but I'm using this small one just to get some reasonable training time so that we can fit that into our lecture. Of course, in practice you will have some large network, and of course I'm telling you that to somehow alleviate the problem or to answer the question that why do we need to make our neural network smaller if we already have such a small neural network. So the reason is pretty simple. I just want to fit all the trainings into our lecture, so I just need to start with pretty small neural network, and of course you can fit that network as it is on the embedded device, but anyway we will make it even smaller. So here is the structure of the neural network. Here you see all different channels and what happens when we get through the convolution, ReLU, convolution, ReLU, and some sort of max pooling. So here you have all these layers. You see the input image, some letter M, and when we get to the end of the neural network and we calculate all that scores, you see that letter M is a champion, so almost 100% sure in the neural network that was letter M. So here is letter S. You see it bears some similarity to number 5. Well, that's pretty reasonable, but it is pretty certain that this is S. And so you can check a few more inputs and see what that is. So so here they are. Good. Here are some more visuals, so we can just try drawing certain symbols and perform recognition, and you see that neural network recognizes what I have drawn with my hand. Now let's get to basically making the neural network smaller. So here we are trying to perform so-called structured pruning. So so here you see what we are doing. So we are copying our model, so just to have 2 models for future comparison, and we are trying to prune all the convolutional layers. So here we have it. So this function gets a model, and amount of the coefficients that we want transformed to zeros. Of course, we will transform to zero the smallest coefficients that we have. We are iterating through all the layers in the neural network. We are checking this is-instance module nnconv2d checks whether this layer is the convolutional layer. So we are pruning only convolutional layers here. If you need some more complicated network or prune some other layers, you will probably need to add some more code. And here we have prune that comes from the torch utils, and we ask it to remove from that layer basing on the weight of the coefficients. And here we have some output that tells us that how many of the coefficients we have pruned. So here you see prune ln structured. This is our layer, some name, amount, how many of the coefficients, what percentage of the coefficients we are removing, some more parameters, performing the removal, and printing what we have achieved. And here you see that we have pruned quite a lot of filters in this neural network. We can do something more complicated. Here is pruning with deletion. So this one, unstructured pruning, is not so interesting because you need some hardware support for sparse matrices. If you don't have that, that won't help you by any means. You will just make your neural network worse. You will just make your quality of your neural network lower, but that won't help you achieve some larger speed or to do something with the amount of memory it uses. While this is the structured pruning, and this pruning can actually remove some layers or some channels from the neural network. That's much more complicated from as you see from this code. And moreover, you are changing the architecture of your neural network, so there are much more places to break something, so the quality of your network may deteriorate. But still, this is a reasonable approach that you can use and get certain results. So let's start it and let's get a little bit through all these code. So here you see the structured prune model function. It takes a model and it takes some amount for some parameter for pruning. Here we have all the old layers. We are checking the device that this model is using. And we calculate some inputs and input and output channels and number of hidden units. So here is performed the calculation of the importance of filters in the convolutional layer. Here we create a new model. So here is the new model, and we are copying the values from the old model to the new model, but the new model now will have some smaller number of channels and layers. And here you see the result. So before pruning we had so this was one input channel, then we had 10 channels, then these 10 channels were transformed once again to 10 channels. Now some filters were pruned, and here we have one channel transformed to 7 channels and 7 channels transformed to 7 channels. Let me show you that in, let's say, in this picture. So here you see one channel, image 28 by 28, that's the input, and here by the convolution it is transformed into 10 channels, 28 by 28. So here is the input, here is the output, and then we had once again 10 channels that were transformed to 10 channels. And the rest of the network is just as it was. So I'm sorry. So here we had ReLU, and here we had another convolutional layer that transformed 10 channels to 10 channels. And then once again ReLU. And here, after the pruning was performed, we have not 10 but 7 channels, so you can think that instead of 10 we have 7. Now these 7 channels pass through ReLU, and now you can think that these 7 channels are entering into the next convolutional layer. Of course, we changed the architecture, so the next convolutional layer now accepts not 10 but just 7 channels and produces once again 7 channels. Here you can see the summary on the neural network, and you can compare it. So what we had before and what we have now. So here's what we had before once again. So we had some input, one channel 28 by 28 that gets through the convolution and transforms into 10 channels 28 by 28. We do ReLU, we do convolution, ReLU, match pooling, and we are having 10 channels all the way down. Here we have one input channel, and convolution now transforms it only into 7 output channels, and we are dealing with these 7 channels until we get to the end. So here's interesting parameter to check. You see the total number of parameters that we had is 93,000, and here we have only 65,000. So something like 30% of the parameters, they were removed from the neural network just by removing few of the channels. So now we have some smaller model. Of course, it may look a little bit strange because these models are already small, but as I told you, these are models, just exemplary models for our lecture, so that we can perform training pretty quick, and and so we need to work with some smaller models. Here I'm trying to assess the quality of what we have, and of course, as you might expect, the quality has pretty deteriorated. So here is the confusion matrix, and nothing remains here on that diagonal structure that we had. We have pretty low accuracy, like 1%, pretty low precision, and so on. Of course, that begs the question, what is this model useful by any means if we have this sort of disaster? But as I told you, after we have performed all that pruning, yes, we have broken our neural network, but we can still a little bit fine-tune it. So let me perform few training iterations with this sort of pruned model. So I will take this pruned model and I will perform just few iterations of training. Well, not even few, just one iteration of training. So you remember we have trained our large model with 3 iterations. Now I'm doing just 1 iteration. So let me do that. And then we will check the quality of our model. I guess this procedure will take something like maybe 3 minutes, maybe 2 minutes. So after the training is complete, we will be back. Welcome back. We have finished our training of our model. I guess we have a small bug when we have just 1 epoch. So we disregard that, but we can start now the part of the quality assessment, and we now may check whether our fine-tuned model is now performing better or not. So do we still have this sort of disaster that we had after removing the layers, or what do we have here? So here it is. So now you can see that our matrix is almost diagonal. So here are the results. We can check accuracy 82, precision 86, and we can compare that not even to this sort of disastrous model after that was assessed immediately after deletion of the layers, but with the original large model that we had here. So here we had 83%, there we have 82%. So yes, we have lost 1%, but we have removed something like 30% of the coefficients from the model. So we had made it pretty reasonably smaller, and we still have pretty decent quality of the model. So that's what we have. Okay. Now let's check some more some more interesting parts. I think we can move now to the problem of the quantization, and I guess the best way you can perform the quantization is the usage of TensorFlow. But our model is not in the TensorFlow format because I have taught you to use the PyTorch. And that was pretty reasonable because PyTorch, I guess, is now used pretty widely, and I'm not sure that TensorFlow will be able to catch up with that. So that's has become a pretty standard of the industry, so that was pretty reasonable. But now we need to convert somehow because TensorFlow has better support for the embedded devices. And it turns out that at the moment you cannot do that just directly. So you cannot just call one function and tell make from PyTorch model make me a TensorFlow model. So instead we should get through some intermediate format that is called ONNX. So here you have this ONNX format, and I will perform saving of our model in that ONNX format. So here are some sort of my files, and I will now run this code, and we might see that a new file, my linet ONNX, has appeared. So we have saved that into the ONNX. So here is some sort of function. So torch ONNX export. I give it a model. I should provide some sort of dummy input that corresponds to the input of the neural network. So here you see the dummy input. I just am taking some random array that has the size that fits into the neural network. So we had images 28 by 28 one channel, and here you see 28 by 28 one channel. So that I give it the file name that I want to have and some names for inputs and outputs. So you can check this code later, and here you see what happens. I use some older version of the offset, and I use some older version of the exporter because the newer version just fails. So nothing we can do. We should use some older versions. And one more thing to notice, this ONNX format, it's not useless as you might guess. The thing is that this format is pretty widely used, so you can use that, for example, on the internet to make your neural network run in the web browser. You can use it in Unity. So if you are creating some sort of games, Unity has some internal can use this sort of format and run models in the ONNX format. So there is some support in the Unity for ONNX format. So it's not useless. This sort of export, it's pretty good. Now let's check it. So I want to load this model, so I will load the my linet ONNX, and let's check the quality because we have converted something. So of course we want to double check that everything is fine and we haven't broken anything. And if we haven't broken anything, we can get to the conversion into the TF Lite format. So while it runs, let me make a small sketch of what we have here. So we have PyTorch, PTH files. We convert them into ONNX, pretty reasonable universal format, and then we will make a TF Lite from TensorFlow. So that's our path that we want to get through. So now I guess we have our quality assessed. Here you see the result. the matrix is almost diagonal. We have pretty reasonable accuracy, like 83%, precision 85, so everything is fine, and we have saved our model into that ONNX format. And we can already use that format in some cases. But now let's get to the quantization. So what is the quantization? First of all, we have in the neural network, we have many different coefficients in different layers. So these may be coefficients in the kernels of the neural network. They can be coefficients in the fully connected layer, so on and so forth. They all are stored in a format of some floating numbers. So that may be float 32, that may be float 64, and so on and so forth. Now we want to compress that somehow. And it turns out that we can transform them into integers and store them in the format of integer numbers that do not consume so much memory. So that may be integer 8, so just 1 byte for a coefficient, or integer even 4 bits for one coefficient. It's still reasonable numbers. So here I'm trying to perform the conversion into the TF Lite. You might see on the left my Lenet TF Lite file appeared, so I have converted that into the TF Lite. And where is basically the quantization? So if we check TF Lite converter from the saved model, I'm asking for certain optimization, and I'm asking regarding some supported operations. And here you see that inference input type and inference output type I demand to be TF int 8. So these are integers with 8 bits for each of the coefficients. So I'm performing this sort of optimization, and I get my TF Lite file. So now it is quantized, and we can use this file on our embedded device. So let me show you. I guess I can do it this way. So I will just list all files that I have, and please check. I have my Lenet ONNX, which takes 374,000 bytes. Here I have PTH that takes 375,000 bytes, and here I have my Lenet TF Lite that takes only 99,000 bytes. So once again, I have pretty significantly shrinked my model so it can better fit into the memory of the embedded device. Now I can load the quantized model from the TF Lite file, and we can assess the quality of what we have there. So once again, we have performed something with our neural network. Of course, there is the probability that we have broken something. To make sure that we didn't break anything, maybe we need some sort of fine-tuning, maybe a few more iterations of training. We need always assess the quality of the model. So now we are starting that assessment, and we will check the confusion matrix that we have, and some different parameters like precision, recall, F1 score, and so on. So here is our matrix. You see it is almost diagonal, so we have a pretty reasonable result, and you see that accuracy and precision have almost not changed. So we still have a pretty decent quality even on this model, despite the fact that we have shrinked this model with already a few different methods. And now the last method, I guess, that we will consider today, that's knowledge distillation. I have already considered the theory behind this process, so let's just get through the code and see how that works. So here is an example, the student model. So the large model is the teacher model, and the small model is the student model. So in our scheme, this large model, that was teacher, and this small model, that was student. So teacher with its outputs teaches student to generate the same outputs. So our student model contains just few fully connected layers. Here you see these fully connected layers. I will show you this representation of the structure. So here we have input 28 by 28. Here we have the first layer that gets the input and generates 784 outputs. Here we get from this number to 128 outputs, and then we get through ReLU, and then we get to 64 outputs, ReLU, and 47 outputs. So that's what we have. Now let's try training this model. So here is a bit of code. It's a little bit convoluted, so I'm not getting into the details. Let me just start the process of training, and after the process is complete, we will be able to assess the quality of the student model and make certain assumptions, certain predictions, whether it's good or not for running on the embedded device. Welcome back. We have finished our knowledge distillation, so we have trained our student network, and let's check how that works. We will even go a little bit further, so I'll try to save the network. Oops, we have no device. Suppose CPU. Okay, we can load it, and we can assess the quality. So here we have the quality of our neural network, and it still looks pretty reasonable. So almost diagonal matrix. Now we have 81, even closer to 82% of accuracy. We started with 83, if you remember, but we have changed our neural network pretty drastically. So here is the result that we have. And while it's training, so here we can check our files. We have student ONNX, and we still can perform on this file. We can still transform it into the TensorFlow format, TF-Lite format, I mean, and then use it on the embedded device. So I guess I will not get once again through all that pipeline with transforming and making all that quantization and so on. We will do that off camera, and then I think I'll show you just how that all runs on the device and what results can we achieve with, for example, Raspberry Pi. So welcome back. We have finished the training process, and I will briefly remind you, so what are we training here? So this is the same student model, so MLP student, but now I'm trying to train it not with the teacher, but on the data we have on our data set. And this is for comparison, because of course you might ask me, why do we need all that teacher if we already have student model, if we know that it fits on the device? So why don't we just train it? And I have already answered that when I was considering the theoretical part. That's because teacher generates more data than we have in our ground truth. Moreover, we can use student model as a substitution not for the whole teacher, but for the part of the neural network, of the large neural network that we consider as a teacher. So you may even have cases when this part is compared not to the output, but if it is compared to some sort of internal representation inside of the large neural network. So I can take output of, for example, this layer and compare it with whatever I have here in a student model, and then replace not the whole teacher model with the student, but some part of it. That's pretty reasonable approach. It still can be done. But what's more interesting, that even using that thing with comparing outputs and inputs, there is still difference whether you train student model on the data set or you train it with teacher. With teacher, you get better results. And here are our results. So first, let's check what happens to the loss. So loss function, it doesn't, barely trains. So you see this plus 3.856. So we have a huge loss, and let's check the quality. So here is the code for the quality. Let me run it, and now we will be able to compare the quality of the student model that was trained on the data set and the student model that was trained with the teacher. So here we have it. You see, here's nothing that looks like a diagonal, so this model, it just doesn't work. So it just doesn't work. So accuracy, something like 2%. Precision, not even 1%. So that's basically the practical reasoning. Why do we need the teacher model? So with the teacher model, even after conversion into the ONNX and loading back, we were able to get these pretty nice matrix, and we were able to get almost 82% of accuracy. That's pretty good, because with teacher we started with something like 83. So we didn't lose much of the accuracy that we had. But in here we have pretty nothing. So it just doesn't work that way. So that's this sort of practical reasoning. Why do we want to do knowledge distillation, not just replace old model with a new model and train it from scratch? So maybe pretty reasonable creating first some large model, training that model, and then creating some small model that will especially fit for your embedded device. Okay, and now with all that being said, let us move to the practical part. So I guess we will change here lighting and some other things off camera, and then I will show you how we can run these networks on the device, and just look how do they work. Here you see Raspberry Pi with the touch screen attached to the Raspberry Pi. So here you see how that looks like, the chip, all the cables that we have here, and here you see the touch screen. So now let me plug in this device. So here you see it starts, or at least it should start doing something. So here we have it. Well, it's a little bit, let's say, large embedded device, because maybe we want to work with a little bit smaller devices. Let me show you for comparison probably one smaller device, just to compare them. Here's for comparison Raspberry Pi Pico, and you can see this one is much larger. The thing is, you can run neural networks even on this one, but that's a little bit more tedious task to do, so we will not demonstrate that on this small board, not on the Pico, but we will use this sort of a little bit larger Raspberry Pi. So let's use it. Here we have Linux installed. We have loaded all our files off camera, so I will just run the appropriate scripts and show you that everything should work. So here we have terminal. I'm entering the folder with the scripts. Here I'm activating certain Python environment that we need to start our TF Lite programs. The thing is that newer versions of Python are not really good with all this stuff, so I'm still using Python 3.11. So here I'm having a demo. This demo in this demo I can input some numbers just by drawing them with my hand, and I can press calculate and get the prediction. So here we have it. I can do some different prediction, for example this one. So I have my prediction 5. Let's draw some letter. Let's say capital A, and here we have prediction A. It's a little bit hard to start it and stop because letters are too small. That was the TF Lite file without any quantization. Let's do the same but with the quantization. So let's do that. Oops. So now I'm trying to draw once again some number, and here we have the number, and here we have the output of the last layer that gives us the probabilities of whether this is a digit or some letter or whatever. Let me draw something different. For example, let's draw letter M. And now I'm pressing calculate, and here we have our probabilities and our predictions. Let's do something more. I don't know, let's do some letter Q, calculate, and here we have it. So that works pretty okay. Okay, so now we have tested our two demos. Now let's check how do they differ in terms of the space they use. So here we have a list of our files, and you can check that where is it, imnist model tf-lite and imnist model quant tf-lite. So one is quantized, the other is not, and you can check their sizes. So one is 377,000 bytes, while the other is almost 100,000 bytes. So it's almost 4 times smaller than not quantized model. So here you see that we can make our model pretty smaller, and it still will work pretty decently on the embedded device. I guess that if we get even a little bit further, we will be even able to fit that model into this sort of tiny device. But of course, that will need some more effort from us, and I guess it's not suitable for just one small lecture. So now we have basically concluded our course on the neural networks, and after watching these demos, we are complete, and we have completed the whole cycle, starting from the definition of what is a neural network, how do we construct that. We have considered different architectures of neural networks, so we know how do we build these neural networks. We have even considered some simple Python scripts that show you how do we do that in practice. And now in this lecture we have even tried to run our network on the embedded device, and you have seen how to do that. Well, it was a pretty decent device, so maybe you will need to run your networks on something a little bit simpler, but anyway, the methods that we have learned, they will be still useful for you. So thank you for your attention, and I hope we will meet in some other courses.